Hello everyone. Today I'm going to introduce decision trees and random forests, which are important supervised learning models. In this presentation, I will explain how decision trees works, why they often suffer from overfitting, and how random forests solve this problem and improves prediction performance through ensemble learning. Both decision trees and random forests belong to supervised learning. Supervised learning means the model learns from labeled data. There are two major supervised learning tasks: regression and classification. Regression predicts continuous value, such as house prices and temperature. Classification predicts categories, such as whether an email is spam or not, or our ages. Decision tree and random forest can both handle regression and classification. So what is a decision tree? It is one of the most intuitive machine learning models, using flowchart-like model for classification and regression. And it splits data based on features to make predictions. Looking at this picture, each internal node represents a question or a condition. Each branch represents the results of that condition. Finally, the leaf nodes give the prediction result. For example, when predicting whether a customer will buy a product or not, the model may first check income, then the customer age, then their previous purchase history, and finally predict whether a customer will buy a product. Decision trees have several important advantages. First, they are easy to understand and interpret. The tree structure is intuitive and similar to human decision-making. It is easy to visualize and interpret. We can clearly follow the branches step by step to understand how predictions are made. This makes decision trees much easier to explain compared to many other machine learning models. Another advantage is that decision trees require very little data pre-processing, and they usually do not require feature scaling or normalization. They can also work with both numerical and categorical data naturally. This makes them convenient and easy to use in practice. Finally, decision trees can capture nonlinear relationships between variables. Many real-world datasets contain complicated patterns that are not linearly separable, just like the one mentioned earlier. Whether a customer will buy a product or not, it is not linear. And decision trees can split the feature space into smaller regions, allowing them to model complex decision boundaries naturally. Therefore, decision trees provide a good balance between interpretability and flexibility. Although decision trees are powerful, they have a major weakness, which is overfitting. Overfitting happens when the model becomes too complex and memorizes the training data instead of learning general patterns. As a result, the model performs very well on training data but poorly on unseen testing data. This graph shows the relationship between model complexity and prediction error. As you can see, as more training data is used and the decision tree becomes deeper, the training error keeps decreasing. However, after a certain point, the testing error starts increasing. This means the model is memorizing the training data instead of learning general patterns. This will result in very high training accuracy but low testing accuracy. This following picture shows when overfitting happens, it will try to reach each and every single point and divide it into the right region. Small changes in the training data may produce a completely different tree structure and result. And this following formula shows the prediction error with bias variance trade-off in machine learning. Deep decision trees usually have low bias, but very high variance, which often leads to high test error, which means it is overfitting. To solve the overfitting problem, machine learning uses a technique called ensemble learning. The idea is simple. Instead of relying on one model, we combine many models together. Each individual model may be weak or unstable, but together they can produce a much stronger and more stable prediction. This idea is similar to the wisdom of crowds, or the voting system. So what is a random forest? Random forest is an ensemble learning method based on decision trees. Instead of building only one tree, it creates many decision trees. Each tree is trained using a different subset of the training data. This process is called bootstrap sampling. In addition, each split only considers a random subset of features. This reduces similarity between trees and increases diversity. Finally, all trees combine their predictions together. For classification tasks, the tree vote for their predictions together. And for regression tasks, the predictions are averaged for the final answer. Now let's look at how random forest actually reduces overfitting. The first technique is bootstrap sampling. Each decision tree is trained using a different random subset of the training data. Because every tree sees slightly different data, the tree becomes more diverse. And the second technique is random feature selection. Instead of considering all features at every split, random forest only selects a random number of features. This reduces correlations between trees and prevents all trees from making identical decisions. Finally, random forest combines predictions from many trees together. Since different trees make different errors, averaging helps cancel out noises and reduce variance. As a result, random forest becomes much more stable and generalizes better on unseen data. Another important advantage of random forest is feature importance analysis. Random forest can measure how important each feature is for making predictions. Features with high importance contribute more to the model's decisions. For example, in a customer prediction system, variables such as age, income, purchase history, browsing history, or education may have different levels of influence. And education can be useless when predicting if a customer will buy a product or not. This is important because real-world datasets often contain such informations that are necessary or irrelevant features. By analyzing feature importance, we can better understand the dataset and simplify the model. In addition, feature importance can help with feature selection. If some variables have extremely low importance, we can remove them to reduce model complexity and improve efficiency. Another advantage is interpretability. Although random forest is more complex than a single decision tree, feature importance still provides some insight into how model makes decisions. Therefore, random forest not only achieves strong prediction performance, but also helps researchers understand the dataset itself. Now let's directly compare decision trees and random forest. Firstly, random forest usually achieves higher prediction accuracy because it combines many trees together. In contrast, a single decision tree is more likely to overfit in the training data. Second, decision trees are more easy to interpret. We can directly visualize the structure and understand how decisions are made. However, random forest contains many trees, making interpretation more difficult. Third, random forest is generally more stable. Small changes in the training data may completely change a single decision tree, but random forests reduce this instability through averaging. And on the other hand, random forest also requires more computation time and memory. Therefore, there is always a trade-off between interpretability, accuracy, and computational cost. Because random forest provides high accuracy and stable prediction performance, it is widely used in many real-world applications. One important application is fraud detection. Banks and financial companies use random forests to identify suspicious transactions and detect potential credit card fraud. The model can analyze many variables at the same time, such as transaction amount, location, and purchase history. Another important application is medical diagnosis. Random forests can help doctors predict disease by analyzing patient information, medical records, and test results. For example, it has been used in cancer prediction and heart disease detection. Random forest is also commonly used in recommendation systems. Platforms such as YouTube, Netflix, or Amazon analyze user behavior to recommend movies, products, or even advertisements. Finally, random forest is also applied in financial analysis and stock market prediction. Although stock prices are difficult to predict perfectly, random forest can still help analyze complex financial patterns and trends. Because of its flexibility and strong performance, random forests remain one of the most popular machine learning algorithms in today's industry. Although random forest is powerful, there are still some limitations. The first one is lower interpretability. A single decision tree is easy to understand because we can directly follow the branches and see how decisions are made. However, random forest contains hundreds or even thousands of trees. As a result, it becomes more difficult to explain the model's decision-making process. Another limitation is computational cost. Since random forest contains more trees instead of just one, the training process requires more computation time. This can become a problem when working with very large datasets. Last but not least, random forest also requires more memory because all trees must be stored. Therefore, although random forest usually achieves better accuracy, there is still a trade-off between performance and computational efficiency. Now, after understanding both the strengths and weakness of these models, we can now summarize the key ideas of this presentation. Firstly, for the decision trees, they are easy to understand, require minimal pre-processing, and can naturally capture nonlinear relationships. However, a major weakness is easily overfitting. When a tree becomes too deep, it may memorize the training data instead of learning general patterns. To solve this problem, random forests use ensemble learning. Instead of relying on one unstable tree, it combines many randomized decision trees together. Through averaging and voting, random forests reduce variance and improves prediction stability. As a result, random forest usually achieves higher testing accuracy and better generalization performance. Although random forests have some limitations, it remains one of the most widely used machine learning models today. Overall, this presentation demonstrates an important concept in machine learning. Combining multiple weak learners can create a strong and more reliable model. This idea has now become the foundation of many machine learning systems. Thanks for listening.